All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're asked this time, let's determine the resultant internal reactions acting on our beam right here at point D. So it's our internal normal force, shear force, and bending moment. If we're doing that, I need to figure out first, what are my support reactions? So I can then come in and slice through at point D and find my internal reactions. So let's start out and do support reactions. If I'm finding support reactions, I need a free body diagram to kind of go along with that. So if I'm looking at this, I have a pin here at A, and then member BC connecting in here. I should be able to identify BC. I only have forces at B. I only have forces at C. If I have a member with forces at only two locations, I have a two-force member. So I'm going to draw a big 2 on here to help me remember that. If this is a two-force member, then I only have one force on this. It should act in a straight line from B to C, or else from C to B. I can guess that. The math will let me know which is right. Really, I'm taking the resultant of CX and CY here and resolving it down to just one force. It just has to go along that member for it to be in equilibrium. So we're kind of able to come in and simplify our work some. Let's draw a free body diagram out. If I come down below, I can say, well, let's just draw our beam. Just a straight line going over. At the far right edge, I need to get in my force here, 150 pounds, going down and to the right, 150 pounds. And that's acting at a 30-degree angle. 30 degrees. I'll label it off to the side. Over the next 4 feet of this beam, I have a distributed load. So 4 feet. It's rectangular and acts down. So we'll just show a rectangle up on the top of this, coming straight down. Our number of arrows don't actually matter on that. Just get some in there. But our height here was 75 pounds per foot. 75 pounds per foot. At C, I'm going to put in, rather than CX and CY from the pin, just a single FBC for this. If I use CX and CY, I could get the right answer. I'm just going to have 4 unknowns on this picture. On my original free body diagram, it's going to make my work a lot harder because I have to bounce back and forth between free body diagrams. If I identify and correctly use this as a two-force member, it simplifies down to just a single force here. I'm going to show it going up and to the left, FBC. And looking at my dimensions, that member goes up and down 4 feet. It goes horizontally 3 feet. Really, that should clue me in that this is a 3 horizontal, 4 vertical, 5 is our hypotenuse. It's a 3, 4, 5 triangle that acts along. So I can label my angle really as the triangle parts in there. 2 feet over gets me to D. If I'm just looking for support reactions right now, though, D doesn't matter for us. So I'm just going to label this is 3 feet. Gets me to A. At A, there's a pin. Pin should always have a Y component. I'll guess that AY goes up. And they should have an X component. I'll guess that AX goes to the right. AY and AX. But then I want to come in and just start finding these. I have AX, AY, FBC, 3 unknowns. I have 3 equilibrium equations I can work with. I should be able to find all of these. So let's sum moments at A. That'll get me FBC first. So with positive going counterclockwise, let's come in and sum up our moments about point A. That should get me AX and AY disappear. FBC's X component won't cause any moment, but that Y component will. It's going to cause a counterclockwise rotation, so we'll add this in as a positive. I want the Y leg of the triangle, 4, divided by the hypotenuse, 5, times the force, FBC, times my distance from A, from the line of action of my force, over to A, would be 3 feet. So times 3. Moment is force, those first 2, times distance. Then we can come in and say, what about this distributed load? Well, it would cause a clockwise rotation, so I'm going to subtract its moment out, minus force is the area of a distributed load. Area of a rectangle is base times height. So our base is 4, that height is 75. Those first 2 pieces are just getting me what's the force in this. I then need what's my distance from A to the midpoint of that rectangle. So I go in 3 to get to the beginning of the rectangle, and then halfway in, plus 4 over 2. Or I can just write that as 3 plus 2, or I'd be fine if people just put in 5 in there. I'm separating it out just to make it a little bit easier to see where my numbers are coming from. 3 gets me from A to the beginning of the distributed load. For a rectangle, we go to the middle, so halfway into it from there. 3 plus half of 4 gets me to that midpoint. And then the very last thing I need is I have to come in and get my y component of this force in here. It's going to cause a moment for everything. So this is going to get me, that will be going down, causing a clockwise rotation, so minus force times distance. Minus, that force is 150. My angle's coming from vertical here, so I want to use cosine to get my y component. Cosine of 30. Cosine 30. That's my force times my distance is 3 plus 4, 7. Is going to get me to 0. If I solve for FBC, I'm going to get the force in member, I can get this over here. The force in member BC ends up being equal to 1,003.9 pounds. That's a 2-force member, so we could say tension or compression for that one, or we could just call it good as is. That would be in tension for us. T. It's not an answer for us, but it's a useful thing. We're going to need that to kind of move forward with everything. From here, let's come in and sum forces in the x, sum forces in the y to get our last 2 support reactions. If I sum forces in the x, I have AX. I'll need to subtract off the x component of FBC minus 3/5 of FBC, 1,003.9. And going to the right, I have a x component of this 150-pound force. So I'll add it in, plus 150. Because that angle comes from vertical, I need to use sine to get that x component in here. So sine, because x is opposite the angle, sine 30 gets us to 0. Which, solving for AX will give us that AX is 527 pounds going to the right. Finally, there's one last unknown for me to get. Let's find AY. I can do that just by summing forces in the y direction. If I sum my forces in the y, I have AY goes up, so AY. I have FBC is acting up, so plus the y component of FBC will be the y leg of that triangle, 4 divided by the hypotenuse, 5, times the force. FBC is 1,003.9. Minus my distributed load. The force from a distributed load, again, is the area. So minus 4 times 75. And then minus the y component of that 150-pound force. Minus 150 cosine 30. Should get us to 0. If I solve that one for AY, I'm going to get a negative number here. AY is a negative 373.2 pounds. That was negative when I guessed that this was going upwards. We're always going to want to use our force as, or we'll label it in here, for support reactions. We'll present it as a positive with the correct direction. So a negative up is really a positive going down. So I should change those around. AY is 373.2 pounds. And instead of saying I dropped the negative here, so I'll change that arrow around. It's going straight down. Always positive with the correct direction. Again, that's my third support reaction. I could also, just to stay in good habits, when I recognize that in my free body diagram, if I'm using that, let's come in and put a dashed arrow going down here. That solid one says this is what I originally assumed. The dashed one's helping us understand, hey, when I use this again, I'm treating it as a positive going down. It's really going down. It removes like, oh, is that going up or down in our work? It helps streamline that and get going with everything. But that's the first setup piece in here. Then I can come in and start trying to figure out, how do I figure out what's going on internally right here at point D? So if we're doing internal forces, I know I'm going to need to make a slice that goes right through point D. So we can come in and say, we're cutting here, slicing right through D. That slice could either then circle around to the right edge of my beam, going kind of through C, we get FBC, that distributed load, our force here, or I could circle around to the left side of that. If I go to the left side of this, all I have to include is this 1 foot free body diagram that has just from A to D in there. It's a pretty easy picture for us to draw and work with. So let's come in and try to get that one up and going. So we'll come up above and make a free body diagram just of the section that we have. So we're going from A out to where we're making that slice in there, right at point D. So label this. This point here is D. I know at A, the left edge of this, I have AX was 527 pounds going to the right. AX equals 527. I have AY in here. Let's relabel that AX so it's not on a different picture. AX equals 527 pounds. I have AY. I originally guessed it went up. I know though it's really going down. So show it going down. We're taking that dashed arrow version of it. AY equals 373.2 pounds. My distance here from A to D is just 1 foot. So 1 foot is our distance. And then internally at D, I need to get my normal force, my shear force, and my bending moment in there. We always want to use our positive sign conventions for these, which tell us we should assume normal force is putting our beam in tension. So we'd have a normal force there at point D, pulling away from our cut. Then because we have this positive sign convention, if it works out to be negative, we just leave it as a negative answer. People should be able to interpret that. We have a shear that I need to put in. Shear should cause a clockwise rotation about the opposite end of our beam from our cut. So if our cut's here, to cause a clockwise rotation about the opposite end, well, that would be at A. My positive shear has to be going down to get a shear at point D, a VD. And then the last one in there is our moment. Should try to curl the beam and make it squeeze in on the top fibers of that beam. If we were actually bending this beam as I curl, if I raise the right edge of that, the top of the beam is squishing together, the bottom is pulling apart. You can kind of picture that if you bend your arms like that. Make like a ring shape here. As I bend up, my thumbs spread apart, my fingers come together a little bit. So for positive, that's really what we're looking for in here. So I could put in a moment on this as well, that internal moment there at point D. Shear, moment, normal force are really the three things I'm looking for. I have a free body diagram that's going to go with this because I'm about to make equilibrium equations again. But let's come in and find those. So I can sum forces in the x direction. We'll start there. Summing forces in the x. I have AX. AX is 527 plus ND is equal to 0. Which if I solve for ND, I get a negative number here. ND is negative 527 pounds. Down below, when we got like a negative on AY, we changed our arrow around, report as a positive with the right direction. Because we have that standard sign convention that says normal force is positive if it puts the beam in tension, here, when we get a negative, people should be able to look at that and go, oh, negative force, that really just means the beam's in compression right there. So we can call it good. We don't need to change that sign around. Use the positive sign convention. ND is negative 527. Then we can sum forces in the Y. If I sum my forces in the Y direction, I'm going to get AY going down, negative 373.2, minus my shear, minus VD equals 0. For this to be an equilibrium, our shear has to be going up, which means we're going to get a negative shear here. That's totally fine. VD, we just leave it, whatever comes out here, is negative 373.2 pounds. Again, because there is that positive sign convention that says what should shear be doing if it is positive, causing a clockwise rotation at the other end, we can work with that. And then finally, our last one. What's MD going to be doing here? So I can sum my moments up about any point to check this one. I pretty much always sum my moments at the cut point, because that way if I messed up my shear, I don't propagate that forward into my moment calculations as well. So let's sum our moments there about point D. This is going to get me the unknown that I have, MD. But the only other thing that I have, and it's going counterclockwise, so I do put it in as positive, I need to get the moment from AY in here. It will also cause a counterclockwise rotation, so plus force times distance. 373.2 force times my distance is just 1 foot, times 1, is equal to 0. Which if I solve for MD, my moment at point D is negative 373.2 pound-feet. And we have a positive sign convention for this, so I need to put a direction on that. But hopefully this was useful for us. If it was, hit those like and subscribe buttons. Stick around. Let's get you in there with JJ.